All right, so here we have this question. For how many non-negative integers n is 1,296 over 2 to the n a perfect p power of some rational number that is at least 1 over 1,000 for some whole number p greater than or equal to 2? So if we want to consider perfect p powers, or at least try to find integer powers of some rational number, we kind of have to do some prime factorization first before we get started with this problem. We know that 2 to the n is already factored. It's for some n, but 1,296 is not factored. We need to factor that. 1,296 is 36 squared. 36 is 2 squared by 3 squared. It's 2 by 3 quantity squared. So squaring that again, you get 2 to the 4th times 3 to the 4th over 2 to the n. And we can use exponent rules. We get 2 to the 4 minus n times 3 to the 4th. So we need to have a perfect pth power. So we need to consider what kind of pth powers we're taking. If you look, we see that the 2's are conditioned on n, but 3 to the 4th is always there. So we need to consider factors of 4. We can't have any 1th powers. Everything is a 1th power. So we're looking at p greater than or equal to 2. So either 2 or 4 will work. So we do cases on p equals 2 and p equals 4. So at p equals 2, we see that this rational number x squared will give you 2 times 4 minus n times 3 to the 4th. So taking the square root, we basically get 2 to the 4 minus n over 2, 3 squared. And so here we let n be equal to 2k, because we know that this has to be, the 4 minus n over 2 has to be an integer, of course. We get 4 minus 2k over 2, which is 2 minus k times 3 squared. And this has to be at least 1,000. And so we use exponent rules to kind of break off this 2 to the 2 minus k power. 2 squared, 2 minus k, 3 squared greater than 1,000. We get 2 to the minus k greater than 1 over 36,000. And so 2 to the k is less than or equal to 36,000. And kind of just using your calculator very easily, if you know your factor powers of 2 very easily, you'll get k is less than or equal to 15. And you can test that, like 1,024 is 2 to the 10th, 2,048, 4,096, 8,192, 6,384, and so on. You get k is less than 15. And so we see that n equals 2k, n is less than 30. And so we need all even numbers basically less than 30. So there are actually 16 solutions here for k less than or equal to 15, because we'll just double that and get our solutions in n. And similarly, you'll do the same thing with p equals 4. We get x to the 4th equals 2 to the 4 minus n, 3 to the 4th. X equals 2 to the 4 minus n over 4, 3. Then be 4k. Then x will be equal to 2 to the 1 minus k, 3. And this has to be also greater than 1,000. And so kind of just breaking things off, similarly as in the first case, we see that 2 to the minus k is less than or equal to 1 over 6,000. 2 to the k is less than 6,000. And that means that k has to be less than 12. You do testing roots again. 2 to the 12th is 4,096, but 2 to the 13th is 8,192. Does not satisfy. And so here, when we double, when we kind of quadruple everything, we have 4k less than 48. We'll clearly get some duplicate roots from the previous, duplicate numbers from the previous case, but we need to count some of the extra cases we get from this case. We see that up to 30, we don't count 32, 36, 40, 44, and 48 for an extra 5 cases. And since we enumerated all the cases, we're done. So 16 plus 5, we get 21 non-negative integers n that satisfy this scenario, this problem, and we're done.
Hi, everybody. This is Tim. Hope you're enjoying our videos. If so, you know what to do. Like, subscribe, turn on notifications, all that sort of thing. But what I'd really want to invite you to do is to send us an email at media@mathleague.org. Tell us which problems you'd like to see us cover next in our video series. Take care and see you in the next video.